Right now, like at this very second, there is a flight computer calculating a linear burn trajectory, and it is meant to slip a multi-million-dollar spacecraft into just this microscopic atmospheric entry window.
Right. Which is incredibly stressful to even think about.
Oh, absolutely. And if that calculation fails, I mean, the ship just bounces off the atmosphere and is lost forever, or, it burns up entirely.
Yeah, the stakes, well, they literally could not be higher.
Exactly. And the wild thing is that the only thing keeping that mission alive, like the fundamental mechanism governing that exact trajectory, is a math equation that you might have learned and probably completely forgot in, like, a high school geometry class.
It really is the ultimate hidden architecture of our reality. I mean, we interact in these equations constantly,
Right.
completely unaware that they are running the show in the background. Whether you are, landing a spacecraft or capturing a 5G signal on your phone or, even rendering the lighting in a video game,
Yeah.
you are relying on the exact same principles of spatial geometry.
Well, welcome to today's deep dive. We are looking at a really fascinating set of curriculum notes today. Specifically, a module titled Day 29 3D Lines, Vector to Cartesian.
Which sounds dry at first, I know.
It totally does, yeah. But our mission today is to take this seemingly abstract mathematical theory, decode it for you, and basically show you exactly how it physically builds the technological systems you rely on every single day.
Yeah, because translating a line from a vector concept into a rigid Cartesian grid is, honestly, it's the key to modern computing and aerospace.
Okay, let's unpack this, because before we get to the rockets or, invisible data streams, we have to establish the basic ingredients of a line in 3D space.
Right, and when you strip it down, it is surprisingly elegant. The source material starts with this fundamental premise that to uniquely determine a line in three-dimensional space, you only really need two pieces of information.
Just two.
Just two. You need a specific point that the line passes through, and you need its orientation. That is it, a starting location and a direction.
Okay, I think most people can visualize that intuitively, but taking that intuitive concept and translating it into a mathematical framework gets complicated quickly.
Yeah, it definitely does.
Especially when the curriculum introduces something called direction cosines. The notes represent these with the Greek letters, alpha, beta, and gamma.
Right.
And I want to slow down here for a second because I feel like this is where a lot of us hit a wall.
Oh, absolutely. The Greek letters scare people off.
Exactly. Why are we dealing with cosines at all? Why can't we just say, like, point the line 45 degrees that way and be done with it?
Well, that's a great question, and it really comes down to how a mathematical grid actually functions. I mean, if you just have a raw angle floating in space,
Right.
it doesn't give a computer any actionable data relative to its environment. The angles alpha, beta, and gamma represent the specific angle the line makes with the x, y, and z axes, respectively.
Okay, so it's about its relationship to the whole grid.
Exactly. An angle alone doesn't give you a usable coordinate. By taking the cosine of those angles, which gives us the variables L, M, and N, we are essentially projecting that line onto the axis using trigonometry.
Oh, I see.
Yeah, we are taking a floating direction and anchoring it to the grid, giving ourselves a mathematical ratio to actually work with.
Okay, so it's basically about finding the shadow that the line casts on the grid.
Yes, that's a great way to put it.
And from those direction cosines, the notes derive our direction ratios, which are represented by the letters A, B, and C.
Right, the lowercase a, b, and c.
Yeah. And the text explains that these ratios are proportional to the cosines. So A is a constant multiplier, k times L, B is k times M, and C is k times N.
Which sounds like a lot of alphabet soup, I know.
It does, but essentially, if the cosines give us the fundamental angle of the line, the direction ratios give us a scalable unit of measurement along that angle.
Exactly. They provide a proportional scale. And these simple ingredients, our starting point in our direction ratios, they combine to create the foundational formula for this entire discussion.
The vector equation.
The vector equation. The formula is R equals A plus lambda times B.
Okay, I want to make sure we ground this formula in a tangible physical reality for you listening, because it can get abstract.
Yeah, definitely.
So imagine you are standing in a large pitch black room and you are holding a laser pointer. You bring your hand up to your shoulder, right? And you turn the laser pointer on.
Okay, painting a picture, I like it.
Right. So the exact coordinate in that room where your shoulder is located, that is your position vector. In our equation, that is A. It is the anchor point where the line begins.
And the orientation of your hand-like whether you are aiming up at the ceiling corner or, I don't know, down toward the floorboards,
Mm-hmm.
that is your direction vector,
Right.
which the equation calls B. That vector B contains those direction ratios we just discussed, the A, B, and C. It completely dictates the trajectory.
So we have our shoulder, which is A, and our angle, which is B. Now, when you switch the laser on, the beam shoots out in a perfectly straight, infinite line.
Right. Infinitely.
Now, imagine sliding a little glowing bead up and down that laser beam. That bead represents any random point that exists on the line.
And in the equation, that random point is R.
Exactly. But if we want to tell the math exactly where that bead is currently located on the laser beam, we need one more variable.
Which introduces the scalar, lambda.
Right. Lambda is the distance you slide that bead along the laser beam. So if lambda is a value of 1, you slide the bead 1 unit forward.
And if lambda is 10, you slide it 10 units out into the darkness.
Exactly. And if lambda is a negative number, you actually slide the bead backward, like passing through your shoulder and behind you.
Yeah, so to find any specific point R in the room, you start at your shoulder A, and you travel a distance of lambda precisely in the direction of B. The vector equation is incredibly descriptive because it basically functions like a set of driving directions. It tells a clear story, Start at this location, face this specific bearing, and walk exactly this far.
It is perfect for conceptualizing the nature of the line.
It is. But as beautiful as that narrative instruction is, it hits a massive limitation when we try to apply it to a fixed, rigid coordinate system.
Now, wait, I actually want to push back on that idea for a second.
Oh, okay.
Let's look at the aerospace application mentioned in the curriculum, right? Space is a vacuum. It is essentially empty.
Right.
If you are flying a spacecraft and you know your current orbital position, your starting point I, and you know the exact angle your thrusters are pointed your direction peg, why can't you just fire the engines?
I see where you're going with this.
Yeah, like why do you need a rigid coordinate system at all? Why go through the computational headache of converting a perfectly good vector instruction into a Cartesian grid?
Well, because in aerospace engineering, you're almost never just flying into empty space.
Fair point.
You are trying to intercept something or avoid something. You are trying to dock with a space station traveling at 17,000 miles per hour, or you're trying to thread the needle into an atmospheric entry corridor.
Right, the target is very specific.
Exactly. A flight computer isn't just asking, what direction are we going? It is constantly asking, will our current path perfectly intersect with this specific set of external coordinates at a specific moment in time?
Oh, wow. Okay.
And the vector equation is terrible for testing intersections because it requires you to basically walk the line step by step, plugging in different values of lambda to see if you eventually hit the target.
Oh, I see. You'd have to blindly slide the glowing bead down the laser beam and constantly check, am I at the space station yet? No, let me slide it further. How about now?
Yes. And that iterative checking would take immense processing power.
Right, which you don't have time for when you're flying at 17,000 miles per hour.
Precisely. So to solve for intersections efficiently, we have to translate the instruction set of the vector equation into a state of being. We have to convert it into a Cartesian equation.
Okay, so the source material lays out exactly how this translation works mathematically. We have to expand the vectors into their structural components.
Right, breaking them down.
We break them down into the standard directional markers on the grid. So I hat for the x-axis, j hat for the y-axis, and k hat for the z-axis.
Yep.
We define the random point R as x, y, and z. We define the starting anchor point A as by 1, y1, and z1, and we define the direction vector B using our scalable direction ratios A, B, and C.
And once we've expanded those components, the algebraic goal, the whole point of this, is to equate the coefficients on both sides of the equation and completely isolate that scalar distance, lambda.
Okay, and when you do that algebraic isolation, you get the Cartesian equation.
You do.
And it looks like a chain of 3 fractions perfectly balanced against each other. It reads x minus by 1 divided by a equals y minus y1 divided by b equals z minus z1 divided by c.
And all 3 of those fractions are universally equal to lambda.
So it creates a universal rule for the line.
Exactly. The Cartesian equation strips away the instruction set and replaces it with this airtight proportional test.
Okay, let's use an analogy to understand how powerful this proportion is. Think of the Cartesian equation not as a laser pointer, but as a complex machine with 3 synchronized gears.
Oh, why like this?
So you have an x gear, a y gear, and a z gear. The starting coordinates, the by1, y1, z1, are where the teeth of the gears interlock, And the direction ratios A, B, and C dictate the specific speed at which each individual gear turns.
That is an excellent way to visualize the constraint.
Right, because for the machine to function, for a point to even exist on the line, all three gears must rotate in perfect mathematical harmony.
Right.
The ratio of the X gear's movement must equal the ratio of the Y gear's movement, which must equal the Z gear. That equal ratio is lambda.
Yeah, they all have to match.
Because if you plug in a random coordinate in space, and the X ratio evaluates to 5, and the Y ratio evaluates to 5, but the Z ratio evaluates to, like, 5.1...
The gears jam.
Exactly. The machine locks up. The point is not on the line.
And that synchronized gear mechanism is exactly what flight computers are utilizing during a linear burn trajectory.
Really. Just that simple proportion.
Yeah, they plug the coordinates of their target, so the space station or the atmospheric entry window, into that Cartesian chain of fractions.
Huh?
If the X ratio, the A ratio, and the Z ratio all evaluate to the exact same constant, the computer instantly knows the burn trajectory is flawlessly aligned.
Wow. So the Cartesian conversion takes the infinite uncertainty of three-dimensional space and locks it into a mathematically predictable grid test.
Exactly.
Oh.
It allows the computer to instantly verify a future reality without having to simulate the entire journey to get there.
But, okay, a rocket is a massive, tangible, physical object that you can track with radar and telemetry. What happens when the thing moving along that mathematical path is completely invisible? Because the sources take this concept out of the vacuum of space and bring it down into our urban environments. Let's look at the second major domain here, electronics and communications, specifically 5G networks.
Yeah, the transition from macro aerospace to telecommunications is where the sheer utility of this math becomes really apparent.
I bet.
When most of us think of a cell phone signal, we imagine it radiating outward from a tower in a giant expanding bubble.
Right, sort of like dropping a stone into a still pond.
Exactly. The waves wash over everything equally. But modern radar and 5G networks don't operate like that at all. To handle massive data loads, they utilize phased array antennas.
Okay, so the notes explain that instead of an expanding bubble, these phased array antennas emit highly directional signal beams.
Yeah.
You can think of it like a tiny invisible lighthouse on top of a building, sweeping a highly concentrated beam of data across a city block.
Right. And the curriculum specifies that the main propagation lobe, which is just the technical term for the core data beam, travels along a strict 3D vector path.
And instantly, we are right back to our foundational spatial geometry.
We are. The antenna array on the tower serves as our starting position vector, A.
The shoulder.
Yes, the shoulder. And the exact angle at which it fires the propagation lobe provides the direction ratio, our vector B.
Okay, so let's walk through the mechanism of how your specific smartphone connects to this invisible beam using that Cartesian formula we've been discussing.
Okay, let's do it.
So you listening, you are walking down a crowded street, holding your phone. Your phone occupies a highly specific physical coordinate in space, a unique X, Y, and Z position.
Right.
The cell tower's computer system needs to know, out of all the devices in the city, is your specific phone intersecting with the path of my data beam?
And just like the flight computer, the network doesn't have the processing time to walk the vector line step by step to see if it eventually hits your phone.
Right, it can't slide the bead.
It has to know instantly. So the network relies on the Cartesian test.
It runs the synchronized gears.
Yeah.
So the system takes the X coordinate of your phone, subtracts the tower's X coordinate, and divides it by the beam's X direction ratio. And it repeats that calculation for the E-axis and the Z-axis.
Yep.
If all three of those independent calculations evaluate to the exact same ratio, if they all perfectly equal lambda, the gears turn smoothly. The system instantly verifies that your phone's receiver is sitting directly on the 3D line of the signal lobe.
And what makes this truly staggering is the computational load we're talking about here.
Oh, it must be massive.
Oh, yeah. The network is performing this algebraic proportion test millions of times a second for thousands of different devices in a given sector.
Wow.
It's constantly recalculating and verifying those fractions as you walk down the street and your physical coordinates change.
That's insane.
The speed required to maintain that connection is entirely dependent on the efficiency of the Cartesian format.
And that requirement for speed brings us to the third major application explored in the curriculum notes.
No.
We've mapped giant rockets and we've tracked invisible data waves, but what about simulating reality itself? Like, what happens when we use this math to construct digital worlds?
The ray tracing.
Exactly. The sources dive deeply into computing, specifically focusing on 3D graphics, rendering, and retracing.
And ray tracing is widely considered one of the most computationally demanding tasks in modern consumer technology.
Which is saying something.
It really is.
Yeah.
When a rendering engine constructs a scene for a video game or a high-end architectural simulation, it builds the lighting in that image by shooting virtual light rays. It effectively traces the path of light backward from the viewer's eye, the camera, into the digital scene to calculate what surfaces that light interacts with, how it casts shadows, and how it reflects.
Okay, so we can map our variables again to this digital environment. The digital camera's focal point, your virtual eye navigating the game world, that serves as the starting position vector, AS.
Right.
And the specific ray of light passing through a single pixel on your monitor is directed along the direction vector, B.
That establishes the line.
Wow.
But understanding the mechanism here is crucial. A modern video game is rendering complex scenes at 60 or even 120 frames per second.
Right.
That means the graphics processor is shooting millions of virtual light rays every single second. And for every individual ray, it has to determine exactly which 3D polygon in the game's architecture it hits first.
And this is where the difference between a vector equation and a Cartesian equation becomes the bottleneck for reality, right?
Absolutely.
Because if the graphics card tried to use the vector method, the start here and travel lambda distance instruction set, it would just crash.
It would freeze instantly.
Yeah, it would have to slide that virtual bead down the ray of light in microscopic steps, constantly running a collision detection script against every object in the room.
Right. Did I hit the wall? No. Did I hit the chair? No.
Exactly. And the processing power required to iterate that search for millions of rays simultaneously is, well, it's just physically impossible for current hardware.
Which is exactly why the source material emphasizes that the conversion to Cartesian components is vital. It enables what they call rapid algebraic calculations.
Right.
By utilizing the Cartesian fractions, the computer completely abandons the idea of traveling down the line.
Oh, really?
Yeah. Instead, it takes the Cartesian equation of the light ray and it algebraically cross-references it with the plane equation of the polygons in the room.
So it's treating it as a pure algebra problem. It's solving for the intersection of a line and a plane simultaneously.
Yes. It's not searching for the intersection. It is calculating the exact coordinate where the intersection must mathematically exist based on the ratios.
That is wild. That algebraic shortcut is the entire mechanism that allows your computer to render dynamic lighting, soft shadows, and water reflections without literally melting the motherboard.
Pretty much. The Cartesian format isn't just a different way of writing the math. It is the structural optimization that makes real-time simulation possible.
It perfectly illustrates how translating a concept into the correct mathematical dialect can fundamentally alter what is technologically achievable.
Absolutely.
So we have spent a lot of time on the theory and the vast invisible applications of this math today. But the curriculum notes don't just leave it in the theoretical realm.
No, they don't.
They end by addressing how a programmer actually sits down and computes this translation. The sources include a computational proof.
Yeah, it's a Python script.
Right, a script designed to act as a literal conversion function, taking a vector input and parsing it into standard Cartesian expressions.
And looking at the specific tools used in this script reveals a whole lot about how computers handle spatial logic. The script relies on a Python library called SIMPy.
Okay, SIMPy.
SIMPy is specifically designed for symbolic mathematics. It handles the algebraic parsing.
And I think we need to clarify why symbolic mathematics is so important here.
Right.
Because when we normally think of coding, we think of numeric calculation, right?
Yeah.
Plugging in numbers and getting a numerical output. But SIMPy doesn't do that.
No, it treats the variables, the x, y, z, and lambda, as abstract symbols.
Right, so it performs the heavy lifting of equating the coefficients and isolating lambda symbolically. It preserves the algebraic structure of the Cartesian fractions before any actual numbers are even plugged in.
Exactly. It allows the computer to understand the algebraic rule of the line rather than just crunching a single instance of it.
It establishes the logic architecture.
Yes. And once that architecture is established by SIMPy, the script utilizes another library called matplotlib for immediate visual validation of the math.
And the notes describe this as an interactive model. This is where the abstract theory finally becomes a real tactile experience.
That's so cool to see.
Yeah. Picture a computer interface with a 3D grid and a set of sliders. When you, as the user, grab a slider and physically alter the starting position coordinates, shifting the by1, y1, and z1, or when you adjust the direction ratios, the a, b, and c, you literally watch the graphical line actively reorient itself in the 3D space on the screen.
Right. The visual output responds directly to the numerical input.
But crucially, as you are shifting that line, you can simultaneously watch the denominators in the Cartesian equations update in real time on the side of the screen.
It's all connected.
You can physically see how changing the angle of your virtual laser pointer systematically alters the synchronized gear ratios required to maintain the line.
Yeah.
It proves that this conversion isn't just like a neat trick on a chalkboard. It is a structural reality that holds up under dynamic computational testing. You are literally watching the invisible architecture of space shift as you manipulate the variables.
It really grounds the entire lesson.
Right.
It demonstrates that mathematical theory and engineering reality are not separate disciplines. They're just different expressions of the exact same geometric truth.
Man, we have covered immense ground today.
We really have.
We started with the most basic, intuitive concept imaginable, right? A starting location and a direction. We saw how direction cosines and ratios project that concept onto a grid to create a vector. We challenged the limitations of those vectors, and we walked through the crucial algebraic translation into the proportional Cartesian equation.
The gears.
The gears. We explored how isolating that one scalar variable, lambda, creates a rigid mathematical test that dictates the life-or-death trajectory of spacecraft, the invisible web of 5G communications connecting our cities, and even the computational rendering of digital light in virtual worlds.
But, as we close out this deep dive, there's one final implication inherent in this geometry that is definitely worth considering.
Oh, what's that?
Well, throughout this discussion, we have emphasized that a 3D line, by mathematical definition, projects infinitely into space based on a definite starting point and a highly precise direction ratio.
Right. The A and the B?
Precisely.
Yeah.
But consider the physical reality of the high-stakes systems we've explored, whether it is a spacecraft aiming for a microscopic entry window or a data beam targeting a specific receiver. What happens in the physical world when that initial position coordinate, that very first anchor point, is just slightly off?
Oh, wow.
Because the line is designed to project infinitely based on that origin. How drastically does a microscopic error at the starting point magnify and compound as the line stretches out hundreds or thousands or millions of miles into the distance?
That is a staggering thought. A fraction of a millimeter of error at the source of the laser pointer translates into a miss of thousands of miles on the other side of the solar system.
Exactly.
The math is perfect, but our physical inputs are always vulnerable to microscopic flaws. That is a brilliant and honestly a slightly terrifying thought to end on.
Yeah, keeps engineers up at night.
I bet. Well, thank you for joining us on this deep dive into the geometry that runs our world. We hope you walk away looking at the structures around you just a little bit differently, and that you keep exploring the invisible architecture of your reality. Until next time.